Hi, I'd like to talk to you about how to write the equation of a polynomial function if you're given some information about that function. In order to do that, I want to start by looking at the graphs of some polynomial functions and a few things that I want you to look for as I give you some examples. Notice that the graphs of polynomial functions are smooth and continuous. And by smooth, I mean a polynomial function could look like this, but it will never come down and take a sharp turn or have a cusp right here. And there are some graphs mathematically that would do that, but polynomial functions do not. And I mentioned they're continuous. That means there won't be any point where they break. For example, you could have a function that comes to here and stops and then begins right above and looks like this. That's a function, but it is not a polynomial function. So our polynomial functions could look like this, but they won't have any sharp turns or cusps, and they won't be discontinuous. Also note, as I'm showing you the examples, that the domain of our polynomial functions is always the set of real numbers. So let's look at a few graphs. Here's our first example. We'll look at this polynomial function, f of x equals x plus 1 times x minus 3 times x plus 2. And we're going to be looking at these polynomial functions in factored form. But if you were to multiply this one out, you would see that the function actually equals x cubed minus 7x minus 6. But for our purposes, I want to see it in factored form. But do notice that this is a third-degree polynomial function. And this x to the third comes from this x times this x times this x. Now let's look at the graph of this function. Here it is. Notice the x-intercepts are -2, -1, and 3. And look up here. Those are the numbers that would make each of these factors equal to 0. -1 would make this factor equal to 0, 3 would make this factor equal to 0, and -2 would make this factor equal to 0. And of course, those are our x-intercepts of the graph, and we also call them zeros of the function. So the zeros for this function are -2, -1, and positive 3. Suppose we were to change the function a little bit and multiply it by the constant 2. So I would have 2 times x plus 1 times x minus 3 times x plus 2. So the only thing we've done is multiplied the function by 2. Let's see what this graph looks like. Here it is. Notice that the x-intercepts are unchanged. We still have the numbers -2, -1, and 3 as x-intercepts or zeros. What did this 2 do? Well, it took the original function and stretched it vertically by a magnitude of 2. Notice we had a point right here, and the little maximum is twice as high on our new function. Here at this minimum value, we stretched it by a magnitude of 2, and now it's down here. Of course, the x-intercepts, or those zeros, are unchanged. When you have a point on the axis, stretching it vertically doesn't change it. That is when it's on the x-axis. Notice this y-intercept was stretched by a magnitude of 2. It's twice as low on the graph of the new function. Let's look at one more. Let's multiply the function by 3. So we'll have f of x equals 3 times x plus 1 times x minus 3 times x plus 2. And here's its graph. I hope you're not surprised by this. It has the same x-intercepts as our original function, but it has now been stretched by a magnitude of 3. This maximum here is now 3 times as high. This minimum here is 3 times as low. This y-intercept was up here, and now it's 3 times as low. But the general shape is the same. The graph started down here, it went up and down and back up for all 3 of these functions. Let's start with this function again and compare it to a slightly different function. Notice the only change is that the x plus 1 is now raised to the 2nd power. But that is going to make a difference in how the graph looks. This is now a 4th degree polynomial. If you were to multiply it out, it actually would be this equation. G of x equals x to the 4th plus x cubed minus 7x squared minus 13x minus 6. But again, I want to focus on the factored form of the polynomial. And notice this x to the 4th comes from this x squared times this x times this x. So here's our 4th degree polynomial, and let's look at its graph. Notice it's still a smooth and continuous curve, but it looks a little bit different. But what isn't different are the zeros, the x-intercepts. Notice they are at -2, -1, and 3. Those are still the numbers that make these factors equal to 0. But here is an important distinction. Over here on this original graph, our 3rd degree polynomial, notice the graph crossed at -2, the graph crossed the x-axis at -1, and the graph crossed the x-axis at 3. Let me label those so we can see them. -2, -1, and 3. The graph crossed at each of those intercepts. Look at this function on the right. Notice that the graph does cross at -2, but then it just touches the x-axis at -1. It's coming from below, it touches, and then it heads back down again. And then at 3, the graph crosses again. And what determines whether the graph will cross or simply touch the x-axis at a particular 0 is the exponent on the factor that 0 comes from. In this one over here, the exponents were all just 1s, and the graph crossed at each of those intercepts. On our function on the right, we have 2 factors that have an exponent of 1 that gave us the zeros of 3 and -2, and notice the graph crossed at 3 and at -2. But the factor x plus 1 was raised to the 2nd power, and that's where the graph just touched the x-axis and turned around. We have what's called multiplicity for each 0. So for the polynomial on the right, our zeros are -1, and we would say its multiplicity is 2. We have a 0 that is 3. It has a multiplicity of 1. The multiplicity is equal to the exponent on the factor that the 0 came from. And -2 also has a multiplicity of 1. And if your multiplicity is even, your graph will always just touch at that 0 and turn around. If your multiplicity is odd, as in the case of the 3 and -2, where their multiplicity was 1, your graph will always cross the x-axis at that 0. We'll look at the function f of x equals -1/3 times x minus 5 times x plus 2 cubed times x minus 1 squared. Now this is a 6th degree polynomial. If you were to multiply this out, it'd take you a few minutes, you would ultimately though have this x squared times this x cubed times this x to the first power, and you can even multiply that negative 1/3 in. So the function would be f of x equals negative 1/3 x to the 6th plus some other stuff. And at this point, it doesn't matter what the other terms of the polynomial are. Let's focus on the polynomial in factored form. Can you tell what the zeros are? Let's list them. The zeros come from the factors that have variables in them. So we look at this factor right here, this x minus 5. Do you recognize that the number that would make that equal to 0 would be positive 5? So 5 is a 0. Let's look at our next factor. We have x plus 2 to the third. Notice negative 2 would make that factor equal to 0, so I have negative 2 as a 0. And similarly, from this factor, I would have a 0 of 1. Now let's talk about the multiplicity. This 5 came from this factor x minus 5, which is to the first power. So the multiplicity is 1. If we look at our next factor, it's raised to the third power. So negative 2 is a 0 of multiplicity 3. And our factor x minus 1 is to the second power. So our 0, that is 1, has multiplicity 2. So let's see what the graph looks like. Here's the graph. Notice it's a smooth curve. There are no discontinuities, but the part I really want you to focus on are the x-intercepts. Again, we call them our zeros of our polynomial. And our x-intercept right here at negative 2, the graph crossed. It flattened out a little bit, and that'll be the subject of another video. Flattened out a little bit, but it definitely still crossed. It was below the x-axis, and it crossed and it's above. Here's our x-intercept 1. It had multiplicity 2. That's an even number, so it just touched there. And right here at 5, our multiplicity was odd, and it crossed. So right here, our multiplicity was even and it touched. At our other two intercepts, the graph crossed because the multiplicity was odd. Let's move on now and come up with the equations. You may have forgotten that was the point of this video, looking at graphs, and now we're going to write the equations of polynomial functions using what we've learned. So here's the problem. Find a polynomial function whose zeros and degree are given. The zeros are negative 1, 0, and 9, and the degree is 3. And notice I didn't say anything about multiplicity, but we'll talk about that. Well, if negative 1 is a 0, it must have come from a factor that was x plus 1. That's how we would get the number 0. And if 0 is a 0, then it must have come from a factor that was just x. And if 9 is a 0, it had to have come from a factor that was x minus 9. So our function could potentially be x times x plus 1 times x minus 9. Now notice I said we would address multiplicity. Suppose we put a 2 right here. Certainly, that polynomial would still have zeros of negative 1, 0, and 9, But notice the degree would no longer be 3 because we would have an x squared times another x times another x. That would be x to the 4th power, and hence a 4th degree polynomial. This is supposed to be just a degree 3 polynomial, so I cannot have an exponent of 2. So based on the degree being 3, we know all of the zeros provided must have multiplicity 1. What I haven't addressed, though, is how about the leading coefficient? How about the number up front? Remember our very first example, that we stretched out the polynomial by multiplying by a factor of 2 or a factor of 1, or excuse me, a factor of 2 or a factor of 3. Would this polynomial also meet the criteria? How about f of x equals 2x times x plus 1 times x minus 9? Would it still have the same zeros? Yes, it would. Would it still be 3rd degree? Yes, it would. So it would also be an answer. Notice the directions said to find a polynomial whose degree and zeros were provided. The answer isn't unique. It could be f of x equals negative 3/11 x times x plus 1 times x minus 9. What we know is that the polynomial function must be x times x plus 1 times x minus 9 with some constant up front. And we don't have enough information to determine what it must be. But since it just asked for a polynomial that met that criteria, I would make it equal 1. It didn't say what it should be, so let's just make it equal to 1 so that it's simpler. And this is our polynomial function. Do pay attention in any problem that you would do, whether you're supposed to multiply it out or not. If I were going to multiply this out, I would multiply the two binomials together first, and you'd have x squared minus 8x minus 9, and we'll multiply that by x. So the polynomial function is x cubed times, x cubed minus 8x squared minus 9x. So our answer could look like this if you want it multiplied out, or it could look like this if you're going to present it in factored form. Let's try another one. So we'll find a polynomial function whose zeros are 2 with multiplicity 1 and 3 with multiplicity 2, and it's 3rd degree. So let's do it. We know it's a polynomial function, so let's use our function notation. F of x equals, and because I see that 2 is a 0, I know that x minus 2 better be my factor, and the multiplicity is 1. So I'm just going to put that exponent of 1 there for emphasis. You don't need to. Now we see that we have a 0 of 3, so that means our factor is x minus 3, and it has multiplicity 2. So we know the exponent is 2. And because it is 3rd degree, we know there are no other factors that involve the variable x. If I didn't have that degree 3, if I wanted to make it degree 7, I could just add some x plus 11 to the 4th power, and it would still have the zeros that were stated. It would have an additional 0, but this is clearly stating that that doesn't happen. So let me erase that. What we don't know, again, is what the leading coefficient is. Is that constant a 1 or a 2 or a negative 17? We don't know, but it just says find a polynomial function. So let's let a equal 1 just for simplicity because we didn't have any other information. So if we let a equal 1, our polynomial function is x minus 2 times x minus 3 squared, and we have it done. If you're required to multiply it out, we could do that, we'd have f of x equals x minus 2 times x squared minus 6x plus 9. It's just good for us to do that. We'll multiply it out. I'm going to distribute the x, and we would have x cubed minus 6x squared plus 9x, and distribute the negative 2, and you'd have negative 2x squared plus 12x minus 18. And when we combine like terms, we would have x cubed minus 8x squared plus 21x minus 18. And it is complete. So again, the answer could look like this if the factored version is okay, or we could write it out this way. Let's look at this problem. Find a polynomial function with zeros 5, -1, and -2, whose graph passes through 2, -108. So that adds a little wrinkle to it because now we have to make sure it passes through a particular point. Well, let's start with the zeros though. We have f of x equals 5 is a 0. That means it must have come from a factor that was x minus 5. -1 as a 0 gives us a factor of x plus 1. And -2 as a 0 gives us a factor of x plus 2. So here's a polynomial with the required zeros. But this polynomial actually wouldn't pass through the point 2, -108. Let me show you what the graph of this polynomial function looks like. Here it is. The graph of y equals x minus 5 times x plus 1 times x plus 2. Notice those intercepts are very clear. Here is -2. Here's -1, and here's an intercept at 5. So it definitely meets the criteria of having those as zeros. But notice it doesn't pass through the point 2, -108. 2, -108 is down here somewhere. So we need to stretch this graph enough so that it will go right through this point. Right? So everything needs to be stretched out. I would want to maintain this 0 and this 0 and this 0, but I want it to be stretched so that it will go right through this point down here, the 2, -108. Well, how do I stretch it? Well, I have to figure out what this constant needs to be right in front. I didn't even write a constant here, but we know that it is some constant a. And our only clue as to find a is the fact that the graph goes through the point 2, -108. That means 2, -108 is a solution to this polynomial function. So if we put in -108 in for y, or for the f of x, and we put in 2 for x, it should make this equation true. So let's do that. So I have this equation. Let's do some simplifying. So I have -108 equals a times -3 times 3 times 4. That is -108 equals -36a. And if we divide by -36, we get 3. So in fact, we do know that the polynomial function will be f of x equals 3 times x minus 5 times x plus 1 times x plus 2. And if we stretched that graph by a magnitude of 3, this point is 3 times lower. Seems about right. And here's our answer. Of course, we could multiply it out if we needed to, but I might present it just like that. Let's do one last problem. Let's write the equation of a polynomial function whose graph is shown. Well, remember, we need to start with those zeros. They didn't specifically say what the zeros are, but we can look at our graph and tell. The zeros are -3 and 2. And notice we also need to determine the multiplicity. Notice the graph crosses at -3, so this one could have multiplicity 1. Right here at 2, the graph just touches and turns back around. It's tangent to the x-axis at 2, so we know the multiplicity is even, so it could have multiplicity 2. So our polynomial function could be f of x equals x plus 3 to the first power times x minus 2 to the second power. But we don't know what this constant must be in order for the graph to go through 4, 9. So let's figure it out. Let's put 9 in for f of x, and we'll put in 4 for x. So we have a 4 plus 3, and we have a 4 minus 2 squared. So I have 9 equals a times 7 times 4. So 9 equals 28a, or a equals 9/28. So our function is 9/28 times x plus 3 times x minus 2 squared. And we have it complete.